Welcome to another Honors Pre-Calculus video. In this video, we're going to be talking about limits and continuity first, and then we're going to move on to rates of change, specifically average rate of change and instantaneous rate of change. Let's start. We're starting with limits. A limit of a function is basically the point which the graph approaches but is not equal to. So if I have this graph, which is y is equal to x squared, if I say the limit as x approaches 2, for instance, what would y approach? Note that for a limit to exist, a point doesn't have to exist at that point. It can be undefined at that point because it's asking what it's approaching, not what it's equal to at that point. So from this side, it's approaching approximately, if you were to create a table of values, you'd see that at 1, it's 1. At 1.5, it's 2.25, and so on until you get around 3.9. From the other way, you get from 3, it's 9. From 2.5, it's 6.25, and so on. If you keep on making values, you get 4.1, which means that by logic, this limit, as it approaches this point, must be 4. Now you could plug 2 into this function and get 4, but that won't work for every function because not all functions have a point defined at that point. Sometimes the limit just asks what it's approaching, not what it's equal to, and those two can be very different in some cases. Now let's get into the notation for limits. To write a limit, you would write lim for a limit, and then underneath that, you would write x, or whatever the independent variable is. In this case, it's x. The independent is x and the dependent is y. So as x approaches is symbolized with the arrow. And in this case, we're going towards when x is 2. Let's say this is f of x is equal to x squared. Then we have limit as x approaches 2 of f of x. Or we can write limit as x approaches 2 of the function itself, which is x squared. You can just write that in there. And it's usually better to write the x squared because the reader will know exactly what function you're talking about instead of defining it someplace and then reusing it at f of x, unless it's a really complicated function with a bunch of fractions and long expressions. Then you can probably define it and then keep on reusing it in different limits elsewhere. Now, to evaluate this limit, you would write equals to and then the value that it approaches, which in this case we determine to be 4. Similarly, is equal to 4. And that's how you would write a limit. Now let's get into some of the algebraic definitions of a limit. To start, we need to talk about one-sided limits. So we have limit as x approaches 2. Now one-sided means that it's either going in from the right or from the left. Now I can start at 0 and go towards 2 from the right. So this direction is to the right. That's why it's a right-sided limit. This is the left-sided limit. I would notate right-sided by adding a small plus above the 2. And now if I write x squared, now I only have to worry about one side, not both sides. So I would say this is 4 still. And for the left side, as you might imagine, it's a negative sign up here. And it's also equal to 4. Now, why does this help us in coming up with the definition for a limit? Well, what did we do to find the limit? We saw that it's around 3.9 from one side and 4.1 from the other side. We were using one-sided limits without calling them one-sided limits. What we can do is we can say that a limit only exists if both its one-sided limits exist and are equal to the same number. Otherwise, you can get something like that. This is a piecewise function, for example, and there'll be a lot of these in limit problems because they always trip people up because it could have a discontinuity. Let's say it's something like this. When you go from the right, it approaches this value. Let's call it 2. If you approach it from the left, it approaches this value, a slightly larger value. Let's call it 3. So since the right-sided limit is 2 and the left-sided limit is 3, these two one-sided limits are not equal to each other. So how would you calculate the limit itself? Well, you can't because it approaches two different values based on what side you're going to. So there's no one limit at this point. Let's try a practice problem now. It's going to be a piecewise function. So f of x is equal to, and then piecewise, we say it's equal to x plus 2 for x is less than or equal to 3, x squared minus 1 for x, 3 is less than x, which is less than or equal to 5, and the last segment is 2x plus 9 for 5 is less than x. So calculate limit as x approaches 3 of f of x, and limit as x approaches 5 of f of x. So feel free to pause the video now and see if you can solve it on your own. Okay, so let's start for the 3. Now, piecewise functions, it's much easier to calculate one-sided limits. With normal functions, you might think, how can you calculate a one-sided limit without calculating the other side as well, because they approach the same side always? Well, with piecewise functions, you just use one equation for one side and the second equation for the other side. So in this case, we're looking at 3. So the first equation is less than or equal to 3, which means we're coming in from the right. So the right-hand side would be just plugging it in, we'll get 5. We could do that in this case because based on a concept we'll learn a bit later, we can always plug in values for certain functions when we're calculating its limits. We'll get to that a bit later though. For now, we know that 3 plus 2 is 5, so the right-hand limit is 5. Now, let's plug in 3 over here. 3 squared is 9. 9 minus 1 is 8. Becomes 8. The left and right hand limits are not equal, which means that this function, or this limit of this function, d and e, which stands for does not exist. Now, let's look at the second limit, which is x approaches 5. So you plug in 5 here, you get 5 squared minus 1. 5 squared is 25, minus 1 is 24. Let's look at the second one, 2x plus 9. So 2 times 5, because we're plugging in 5, 2 times 5 plus 9, which would be 10 plus 9 or 19. Again, this function, or this limit of this function, d and e. With piecewise functions, you'll get a lot of does not exist because a lot of them are discontinuities. So in this case, both of them were discontinuities. Now you might be thinking, well, it's 5 is less than x, not 5 is less than or equal to x. So you physically cannot plug in 5 into here because the function at this equation does not exist at that point. Well, since it's limit, not value, it's what it's approaching, not what it's equal to. So as we mentioned previously, we don't need a point defined at that point. We can just find the nearby points, and we can also do that by plugging in the value into this equation. All right. Now we've got another problem. In this case, it would be a polynomial that looks something like this. Based on the graph instead of the equation, find the limit. In this case, we're going to be going towards limit as x approaches 4. What would you use? Again, feel free to pause the video. For a graph, it's about as easy as an equation. You just look at the graph and find out where the function is defined, especially for a polynomial. We'll get right into that later, why we can do that for a polynomial. And if you were to draw a line, you would see that it's about 2, but 2 is actually up here. So maybe 1.8 would be a better approximation of the answer. For graphs, unless it's given a clear graph with the grids and proper scaling, it'll always be hard to find the exact value. So we approximated in this case to 1.8 or 1.7. Okay, our next topic is continuity, and that's why we can just plug in values or look at just a point on a graph for polynomials. Continuity is basically informally defined as being able to draw the graph without lifting your pencil. I can do this and I won't lift my pencil. But if I do that and then switch here because there's a break, then I am lifting my pencil. If there's a hole in the graph, I am lifting my pencil. If there's an asymptote, I am lifting my pencil. So there are 3 main types of discontinuities. A hole, which is a removable discontinuity, a jump, which is a jump discontinuity, and a asymptote, which is an infinite or asymptotic discontinuity. And we've talked about most of these before, especially in our rational equations and functions unit, because we talked about asymptotes and holes in them. So the only other one is jump discontinuity, which we talked about when we talked about piecewise functions. So what is the formal definition of continuity, though? The formal definition of continuity is made up of 3 parts. The first part is that the function physically has to exist at that point. Let's call it a point C. It has to exist at that point. Unlike limits where it can just not exist, it's just what it approaches to, it has to exist for a continuity. Otherwise, it'll be a removable discontinuity. The second one is you have limit as x approaches C of f of x. That exists as well. The reason why is because if the limit doesn't exist, that means it's a jump discontinuity, because you have something like that, which is obviously not continuous. And the third part is 1 must be equal to 2. Now, I don't mean that like the number 1 and the number 2, but in this list, f of c must be equal to the limit as x approaches c of f of x. This is because if you have a function like this, but there's just this point up here, instead of being with the rest of this graph, it still exists at this point. The limit still exists, but the limit and the function point are not equal at this value, which means that it's not continuous. So you are given that all polynomial functions will be continuous. That is the main one that you should know. There are some other functions that will also be continuous always, but polynomials, you can always plug into them, unless there's a piecewise function or a hole or something. Rational functions you usually cannot just plug into it because there's usually a hole or an asymptote. Okay, we're done with the first half of this video. The second half is talking about rates. This half will probably go a bit quicker. There are 2 main types of rates of change: average and instantaneous. First of all, rate of change is basically the slope. When we talk about lines, the slope is the rate of change. But what about for other functions? Well, we can use either average rate of change or AROC, Or we can use instantaneous rate of change, or IROC. The A in AROC is average, then rate of change, instantaneous rate of change. So average rate of change takes 2 points and connects them with a line called a secant line. This is a secant line, and you find the slope of that to get the average rate of change. So the definition of it is basically f of b minus f of a over b minus a. And this is saying that this is a, this is b, so the function values of that would be f of a and f of b respectively. So this is the formula for AROC. IROC is a bit more complicated though. IROC is trying to find at this point A the tangent line which intersects it only once, as opposed to the secant line which intersects the curve twice. In circles, in geometry, when we learned about circles, the tangent intersects the circle only once. The secant intersected it twice. This is the same thing with curves. The slope of the tangent line is the IROC, and the way you would figure that out is you would use secant lines that are very that are moving towards this one point. So you would say that you have another point at a plus h, where h is a small value, then h decreases and h decreases until h becomes 0. But when h becomes 0, you don't have a rate of change anymore, which is why we don't have the value at h equals 0, we use it as h approaches 0. That sounds familiar, doesn't it? We're using limits for this. We say limit as h approaches 0, but now what? We're basically taking the AROC until h equals 0, and when h equals 0, where the AROC doesn't even exist. In this case, it'll just be 0 because 0 over 0, which doesn't exist. But we would try to simplify this down until you can plug in h equals 0. So the formula would be the same as this, but b we can write as a plus h because we're just moving h in one direction. And then it'll be a plus h minus a, which just simplifies down to h. So you take the limit as h approaches 0 of this, and most of the times it does exist, especially for polynomials. So let's start with an example. Let's say we have a function f of x is equal to, let's use x squared again. And let's say we want to calculate the AROC from 2 to 4. Well, AROC is simple. You would just plug it into the formula, which is f of 4 minus f of 2 over 4 minus 2. So what's f of 4? That would be 4 squared, or 16. F of 2 would be 2 squared, or 4. So it'll be 16 minus 4 over, and then we just do b minus a, which is 4 minus 2. So 16 minus 4 is 12, 4 minus 2 is 2, so 12 divided by 2, or 6. That would be the average rate of change from 2 to 4. Now, let's find the IROC at 2. In this case, the IROC would be limit as h approaches 0 of f of a plus h. So in this case, it'll be 2 plus h squared, because f of x is x squared, so if it's 2 plus h, we just do 2 plus h squared, minus 2 squared over h. Now, this might not look like much. You might not think it's simplifiable at first, but you can expand the 2 plus h squared. So you'll get limit as h approaches 0. It's important to always write limit as h approaches 0 in front of every step until you're able to plug in h as 0 without creating a 0 by 0. In fact, if we plug in h over here, we get a 0 in the denominator, and 2 plus 0 squared is just 2 squared, so 2 squared minus 2 squared is just 0, so we do get a 0 by 0. Now let's expand it. We have 2 plus h squared, so it's 2 squared, which is 4, plus 2 times h, which is 4h, plus h squared. and then minus 2 squared, which is 4, divided by h. Now we can cancel off this minus 4 with this 4. 4 minus 4 is just 0, so it cancels off. Again, we write limit as h approaches 0 of, in this case, we just get 4h plus h squared over h. And now you can simplify it. So we get, there's always an h in the numerator, so we can cancel it off with the denominator. So we get limit as h approaches 0 of 4h divided by h is just 4. H squared divided by h is just h. Finally, we can plug in h is equal to 0 because when we plug that in, we get 4 plus 0, which is 4. And that would be the instantaneous rate of change at x equals 2 for this function. And that's AROC and IROC. We calculated both AROC and IROC for this function. And that's it for rates of change. At the end of pre-calculus or the start of calculus, we will go more in depth into limits and rates of change, as well as area, which we talked about a while ago.